Howdy, this is Jim Rutt, and this is The Jim Rutt Show. Listeners have asked us to provide pointers to some of the resources we talk about on the show. We now have links to books and articles referenced in recent podcasts that are available on our website. We also offer full transcripts. Go to jimruttshow.com. That's jimruttshow.com. Today's guest is Lynne Kiesling. She's an economist focusing on regulation, market design, and the economics of digitization and smart grid technologies in the electricity industry. She's a research professor in the School of Engineering, Design, and Computing at the University of Colorado, Denver, and she's co-director of the Institute for Regulatory Law and Economics. Lynne also provides advisory and analytical services as president of Knowledge Problem, LLC, and she's an adjunct professor in the Masters of Science in Energy and Sustainability program at Northwestern University. You got a lot going on there, Lynne. Welcome to the Jim Rutt Show.
Thanks, Jim. I'm happy to be here. We do have a lot going on. Lots for us to talk about.
Indeed. I met Lynne at an event at the Santa Fe Institute where she gave a very interesting presentation, even though it was relatively short within the time constraints of the program that we were both on. So I thought I'd invite her here and we can do a dive into one of my favorite domains, which is the electrical grid and the things that are happening and should happen, but might not, to the electrical grid in the years ahead. One of the things that's particularly interesting about electricity as a product is it's got a useful life of about 1 microsecond. It gets generated and then either distributed and used or put down into the ground. At least that was the case before there was any form of storage. What are some of the other interesting things about electricity as a product category?
Well, I think if I can build from your physical grounding there, pun definitely intended, the fact that it is really only useful for about a microsecond means that when you think about it at a kind of transactional layer, supply and demand have to be in real-time balance at all times. And so that has some pretty serious implications for how we designed the grid back in the late 1890s after. And I don't know if you want to talk about, Tesla and Edison and Westinghouse.
Nah. Well, we don't need that. We don't need that ancient history. Y'all can look it up. Tesla won. I gave you a spoiler there, folks.
Accompanied by one of my favorite Pittsburghers, George Westinghouse. So yeah, but for the past 130 years, the architecture of the grid is, because of the alternating current nature of it, requires real-time balance between supply and demand. And what that meant in a time of mechanical systems and analog controls is that you needed to have a big central control room in order to achieve that supply-demand balance. And so you have an engineer in the control room kind of flipping switches and twiddling dials to keep that balance in check.
Yeah, and that is a very interesting thing, because if you think about it, say a large-scale grid, several states, there are consumption points coming on and going off all the time. You turn on your electric stove, you just flicked on a little pull on the grid, and not quite as volatile, at least not until recently. On the supply side, generators are coming on, going off, having unexpected outages, having scheduled maintenance, et cetera. So there's this very crazy dance going on between demand and supply that's got to be balanced down to the microsecond, or whatever's left over has to be grounded out into the ground. Yeah. I don't know how much is grounded out anymore, but I know it was a non-trivial amount back in the old days.
Yeah, I've lived in Chicago for most of my adult life, and we infamously had what were two of the early pioneering big power plants from Sam Insel, Fisk and Crawford, that by the 1990s, the city had grown out to where the plants were located. And so there was a lot of environmental problem associated with those neighborhoods. But the other thing that was really a problem was that when they had excess generation, there were periods where they would just boil the water that was in the, in the branch, in the channel going down to the Illinois River. So yeah, I think storage is going to definitely reduce our waste, right? Because that's really, really wasteful, both physically, environmentally, and economically, to be, putting all the resources into generating this valuable product. But at any point in time, if you have excess, so it really isn't valuable in that moment, then you waste it.
Yep. And then, especially, again, this is the old days picture, which we still sort of live in. There was basically two kinds of power generation. There's base load, which is big hunkin' power plants that take quite a while to start up and shut down. And then there's so-called peakers that they can be turned on and off more rapidly, some of them quite rapidly, some of them almost instantaneously, but not quite. And typically the base load guys are like coal plants or oil plants, not there's very many of those anymore, and nuclear plants. Hard to start up and shut down for a number of reasons, but they're quite economically efficient, at least if you don't count the externalities costs of CO2 for the coal plants. And then the peakers are, they're things like, used to be diesel engines. Now a lot of them are natural gas, and hydro can also be a peaker if it's designed correctly. So, as you start thinking about, the loads coming on in the afternoon, everybody's coming home from work, getting ready to fire up their kitchens, et cetera, or a hot day where the air conditioning is going to be a big demand. All the peakers start to come online based on some rationale on, I suppose in theory at least, on the ones that are most efficient coming on first and the least efficient coming on last. Is that a kind of a tolerable cartoon version of peakers and baseload?
Yeah, I think that's a pretty good summary of how it works. Let me layer on some of the economics of why it is that way. The big honkin' power plants, the central station, large scale generators like nuclear and big coal-fired power plants, they have very high fixed costs. They're very capital intensive. So it takes a lot of assets to build these things. But then once you've built them, the actual additional costs that you incur to generate an additional, kilowatt hour of electricity is really small. So it's basically your fuel costs and some labor and a little bit of other, some other stuff. But it is just dwarfed by the capital cost, the fixed cost of constructing the plant itself. And that means that those big power plants have something called economies of scale, which means that at least, for some large amount of demand, that if you have just one plant generating all that electricity, that's going to be the lowest average cost way of doing it. And so that's why you get this concentration in the early 20th century. And I mentioned Sam Insel. He's one of the guys who really pioneered and pushed, General Electric and others to engineer these big power plants. And it really did transform the economics of the industry. And we have that to this day. But the trade-off of that, as you say, is that it takes a while and it takes a lot of effort and a lot of cost to spin those guys up. And so, in other words, they're what we call slow ramping generators. So, you don't ever want to turn those things down except for when you have to for maintenance. So you want them to run, as flat out as possible, because turning them on and off is extremely time consuming and costly. Whereas for peakers, it's more like turning on and off a jet engine. And in particular, since the 1980s, the combined cycle gas turbine, which uses natural gas, is extremely energy efficient and has about half the greenhouse gas emissions of a coal-fired power plant. And it literally is a jet engine that you could just, hook up to in a power plant and just turn on and off as needed.
Got it. But now things are getting more interesting. Tell us about distributed energy resources.
Well, this is, I think of this transition as, we are starting to socialize the idea of calling it an energy transition. And so this energy transition that we're in is fascinating because, we're coming from this very early 20th century notion of the electric utility as this kind of vertically integrated system. And that was Edison's idea. Edison was like, we're building a system and, it's all integrated from the generator through the wires. And for him, it was even into the lighting fixtures inside the home. And that, to some degree, I would argue, came from technological necessity, that those mechanical and analog machines all had to work together and be coordinated with humans in the loop, so to speak. And so there's two big areas of technological change that we've been having since the 80s. One is the big changes in generation technologies. The combined cycle gas turbine, jet engine on platform is one of them. But then in the 90s, there was really substantial innovation in wind turbine technologies. And so that's one reason why wind power has proliferated the way it has, is that the production costs have fallen and wind turbines have become so much more energy efficient because of a lot of innovations that happened in the 90s with the long blades, some of the composite materials that are used to make wind turbines, the way that rotors are made. There's all kinds of pieces parts that go into a wind turbine, and they've all gotten better and improved energy efficiency. And so that means that we have more distributed wind turbines. And so that's good from a low carbon perspective. But both the gas turbine and the wind turbine are kind of larger scale, what I guess we would call utility scale type technologies. Since what has really gotten interesting in, I guess I would say, the past 15 years has been the falling production costs for solar photovoltaics. And solar PV is a kind of mid 20th century technology. It started, really, really small as part of the Apollo missions. And only more recently has it been used, since the 1970s, to generate electricity for some use other than just on spacecraft. And so that's a much more demanding use. And so there's been a lot of innovation recently. And in the past 10 or so years, the production costs for PV panels have plummeted, 60% in the past decade. And there's a lot of interesting dynamics there. Some of it is just kind of natural innovation and entrepreneurship. Some of it is policy driven, and those two intersect. But once you have that and you can have more distributed rooftop solar panels, that's when we get into what you referred to, this idea of distributed resources. And so with PV, you have this distributed ability to generate low carbon energy. And I say low carbon, not zero carbon, on a life cycle basis, because of course the process of producing PV panels is energy intensive. So that's still a work in progress from a carbon perspective. So we've got the kind of distributed PV that can go on the roof of your house, the roof of your garage, as a canopy over a parking lot, and kind of make use of unused roof space or airspace to generate electricity. And then the other really important distributed energy resource from a complementary perspective to this is the electric vehicle and battery storage. And I put those two together because essentially, an EV is just a battery on wheels that provides you two types of value streams. One, it can store energy, and two, it can transport you places you want to go. But otherwise, the EV and the battery have a lot of similarities in terms of being able to spread production and consumption, spread demand and supply, and balance them out over time. And so that really helps. Storage is the holy grail in the grid. It's the thing that gets you out of that problem that you mentioned of having to have that microsecond balance. And so these distributed resources are really now coming into their own economically and physically.
Yeah, and of course, not only are they distributed, but they're also intermittent, right? There are times when the wind doesn't blow, and guess what? All night, solar doesn't do anything. And even during the day, during cloud cover, it can fall quite considerably. So, and that can be quite localized. A big old thunderstorm goes across a big solar farm, for instance, right? Oops. Big fallout in production, and of course, wind can vary. It's got trend lines. You can predict it some ways in advance, but it can come and go as well. So that not only are they distributed, which is quite different than the big giant plants that everybody knew where they were and what they were doing. And if you had to, you could talk to them on the phone, find out whether they were up or not. But these things are, scattered every which way and are constantly going up and down and losing and gaining productive capacity.
And that variability, I think over the next few years, that will turn from a bug into a feature. But if you put yourselves in the shoes of kind of a 1960s era distribution system control room engineer, operator person, and you think, okay, I have to coordinate, I have to control what's going on the grid to balance supply and demand. And I have these big generators and they're always running, and I just have to basically tell them to ramp up and down a bit over a certain amount of time. And that's a very, very different problem from what you just articulated. And so I'm not an engineer, but the engineering challenge of this is substantial. And it's one of the things that I think is causing a lot of consternation in the industry and a lot of hesitation about distributed resources. Is the kind of, we don't know how to dispatch those things. We can't dispatch those things because they're intermittent and they show up when they show up, and we can't dispatch that way. And so part of what's going to have to happen, I think, is a cultural rethinking of the process of operating the grid as the grid becomes more heterogeneous in its resources and in its behavior. But that's a real tricky challenge for the engineers.
Yeah, I understand also that the way the grids were designed makes perfect sense. Like, say, the lines coming into your house, the assumption was the power was going in, not coming out. But now, where people have rooftop solar or occasionally wind, they could be moving large amounts of power, maybe even more than their house normally consumes, back out into the grid.
Yeah.
So that's an unanticipated change in network topology.
Yeah, exactly. And that's the change in the nature of, if we want to think in terms of like network topology and think about the grid as a system. And so I'll just start by saying system, although I have an idea of where I want to go with this. But I'm sure we'll get there. The agents in the system, in the kind of 20th century architecture and 20th century network topology, producers are producers. They have these large scale generators. All they do is they push current on this one-way flow in the direction of consumers. And the consumers might be a big factory or an office building or a hospital or an apartment building or a house. So there's industrial, commercial, and residential customers of different sizes, but that's all they are, is consumers, right? It's just, as you say, the power's coming in, I flip the switch and the light goes on. And in that 20th century landscape where the technology and the regulations both combined to sell electric service to customers as a commodity service, right? I flip the switch and the light goes on. They're all just electrons. I don't care as long as I have, as they say, cold beer and warm showers. So that's the kind of 20th century landscape, and regulation fed into that by embedding this form of pricing to customers that was basically a fixed rate price. And so what the electric utility would do is they basically estimate their costs, report their costs to the regulator, plus a rate of return on their assets. And that all gets wrapped up in what's called a revenue requirement. And then you go through this elaborate calculation to figure out the price to charge to those three types of customers, industrial, commercial, and residential, that when you add up the expected revenue, it exactly equals the utility's total cost. And so total cost equals total revenue, average cost equals average revenue, and the prices that customers paid were fixed.
Yeah, and even by time of day also, right? Everybody, if it came out 7 cents a kilowatt hour, that's what you paid, 3:00 in the morning or 5:00 on a Friday afternoon.
Exactly. And I think you're mentioning the time difference for a very important reason, that the actual value of what you're consuming, the value of the electricity, differs considerably from 3 in the morning to 5 in the afternoon. And also the cost of producing it, right? At 3 in the morning, when most everyone's asleep, you crank up that big nuclear power plant and your marginal cost is very, very low. And so the cost of producing that kilowatt hour at 3 a.m. is really low, but the value is also low. But you're paying an average price. At 5 p.m., it's the exact opposite. The cost of producing that kilowatt hour is high, both in terms of resources and also in terms of the emissions impacts. But the value to you of that 5 p.m. kilowatt hour is high because that's when you need your air conditioning, but you're still paying that averaged price that's lower than your value at that time. So you have this mismatch between price and value by doing this averaging.
Yeah, and particularly now that we have these intermittent sources that are relatively strongly correlated with the diurnal cycle. The wind is on average stronger at night, not by a lot, but by a bit. And of course, solar goes to Zippo at night. So, we have now this temporal pattern. We always had a temporal pattern of usage, and now we have a temporal pattern of supply to lay on top of the temporal pattern of usage. And it's not all that well correlated. The solar better correlated than the wind, but some definite non-correlations there as well.
Yeah, and that's one reason why storage has always been the holy grail and continues to be, because if you can capture that inexpensively produced wind power at 3 a.m. and then save it up and use it in the morning, then that's both economically and environmentally, that's very beneficial. The other thing that's I think going to be a really seismic architectural shift is, in this 20th century world where you've got these big generators and it's just this one-way flow from generators to customers. And as customers, we're all paying these fixed average rates. What that means is, from an architectural and operational perspective, the way you run the grid is that you ramp the supply up and down to make sure it meets demand. And so that means that you do a lot of demand forecasting, or what's called load forecasting, to anticipate as best you can what demand is going to look like, in half an hour, in a day, in a week, next year, right? So you do a lot of this demand forecasting so that you can get the supply resources lined up and it's called resource adequacy, to be able to meet that demand. But now, as you say, with these intermittent resources, supply is going to be more variable, and it might be both economically and environmentally beneficial to let supply vary. But then what does that mean? That means that if supply is varying, then what you need to be able to vary demand to meet supply, as opposed to varying supply to meet demand. And so I think that's going to be a pretty big seismic shift in our thinking of how we run the grid.
Yeah, I remember when I think California was it the first big grid to go to time of day pricing for residential customers. It was like quite a while ago. And, I knew of people that were setting their dryers to run at 3:00 in the morning for that reason. We can, of course, do a whole lot more than just that.
Right. And I think California, during the California energy crisis 2000-2001 period, there was a period when San Diego gas and electric customers could see a real-time price. And it was, I think, as someone who is very strongly in favor of dynamic pricing, it was a little bit not ready for prime time, but it was there. They did it, and yeah, it's you schedule what you can to happen at 3 a.m, and I think you learn very quickly just how much variation there is in the cost of generating electricity over the course of the day, which of course most people don't think about because we're just habituated to think, okay, it's always there. I have to flip the switch and the light goes on, and I don't have to think about it any more than that. But I'm actually in Chicago. I'm on the utility there, ComEd, has a residential real-time price rate, and that's what we're on. And I have a digital thermostat, which I could program. There's this if this then that little plug-in algorithm that I can program into my thermostat to make it price responsive. But I haven't quite debugged my code yet.
And of course, we know that only 0.1% of people are ever going to do that. So the thermostats need to have that software built in. You just throw a switch and say, run algorithm B, for instance, right? That's how these things will actually go to market. Toggling in the program into your thermostat, not going to happen too often.
Right. And I think the automation, and this gets us, to kind of fast forward to the other of the two big areas of transformational technology. One is the generation technologies that we've been discussing, and especially the distributed resources, and then the storage that we can use to save it up and shift it intertemporally. But the other big area of technological change that's part of the energy transition is digitization. And since the mid-2000s, first it started as smart grid, and then it became grid modernization. And the digitization of the electric grid has been going on for about 17 years, slowly, incrementally. And, digital meters, the smart meter for to meter your consumption at your home is one type of technology to do that. But then, on the inside of the grid, the guts of the grid, whether it's in transformers or substations or the ways that you can do fault detection and automated repair even within the wires network itself. And then there's and I think this is not my area of specialty, but I think there's an area, and it's mostly high voltage focused, is something called dynamic line rating, which is a way that you can use digital sensors to monitor current flow in real time and to see essentially what the capacity is of a given wire. And that if it's operating at less than full capacity, you can re-rate the line to be able to have more flow one way or the other. And so essentially you can increase the total flow of the wire by doing this digital dynamic line rating. So, yeah, that's pretty cool.
Now, just for a point of information, today, if somebody has rooftop solar at their house, is it communicating in real time back to some control center, or are they just dumping their electrons into the wires?
It depends. There is a couple of years ago, the IEEE issued a digital inverter standard. So, if you have solar panels on your roof, the solar panels capture the sun's rays and turn that into basically create electrons. But the current that comes out of that is direct current. And so in order to get the electricity from your panels onto the grid, you have to change that direct current to alternating current. And so you have to go from a line to a sine wave. And that means going through an inverter. And now IEEE has these standards for digital inverters to, as far as I understand it, make that physics handshake a little more straightforward and easier to monitor, and easier to just interconnect those resources onto the grid without it being disruptive. And so some of them, if they have those digital inverters, there's a lot more visibility into what your panels are doing. And I don't know how widespread those are in use. We're definitely in a transition process on those, because I think otherwise it's, you just put your excess generation out on the grid, And I think there's each panel installation has a physical limit, that you can't put out more than a certain amount, because and the distribution system engineers will set that so that it doesn't cause any disruption to the rest of the grid.
Yeah, got it. That's interesting. Now, when you think about, systems and systems mediated by computers, if the rooftop solar system and its inverter is sending useful telemetry back up the network, doesn't do any good unless there's the right software on the other end to make sense out of it. And as a person who spent much of their career building large scale systems for industries, not the electrical industry, more financial services, and then later the internet itself, we know that sometimes these big players, their software technology can be really behind the times. How are the people who are managing the grid these days with respect to the currentness of their software and their ability to take advantage of this new telemetry that's coming at them?
Yeah, I think your use of the word telemetry is exactly right, and almost immediately gets beyond the extent of my expertise. But it's important because the coordination, right? The coordination that has to happen in the grid is very much about phase angles and keeping the angles, because we're talking about waves, keeping all these angles and within certain ranges so that you don't disrupt the sine waves. So I think it's been a challenge over the past 15 years, but increasingly, a big part of the, within the utility focus of the grid modernization and smart grid has been building that software capability so that they can take advantage of all these digital sensors and, be able to have more visibility into what's going on in the system and to have more fine-grained control of it. And I would say different utilities are moving with different speeds towards this. And it's definitely still a work in progress. But then you also have, at the kind of bleeding edge part of the continuum, you can have things like substation virtualization, where you take your substation and you create a digital twin of it, and you can use that to manage what's going on in your substation. So, it reduces the amount of time you have to spend rolling crews out to go maintain things out in the field, that you can do more remotely. And that, and sort of the famous things that people will say about the digitization of the grid is, that certainly when I was a kid, a squirrel falls in the transformer out, in your backyard, and your lights go out, and it, but the utility doesn't know it. So you have to call them and say, hey, my lights are out. And even to this day, at least now, we tell them on Twitter as opposed to having to phone them up. But they are getting more visibility into knowing when and where there are outages. And so the digitization is really good for reliability outcomes for customers. So getting a more reliable service.
I got to tell you a funny story about that. Here in Virginia, where I live, before they renamed themselves Dominion Power, our local statewide electrical utility was called Virginia Power. And it turned out there was a poor woman who that was her name, Virginia Power. And when the lights went out someplace, people would call directory assistants, and some percentage of the operators, that's how far back in time it was, this was operators, would give them the number for poor Miss Virginia Power. I don't remember what she did, but it was quite a mess, right?
Oh, after the invention of the answering machine, whenever there's a storm, I would just, turn off my ringer and put the answer machine on to say, no, I'm not that Virginia Power.
Call this number, please.
Right. Right. The other area of digital technology that I think is really important is on the other side of the transaction, if you will, is on the customer side. So, we've been talking about the kind of within the guts of the wires, the digital sensing and monitoring and automation in substations and transformers, and the implications of that for the control room and software. There is, I should actually say, as long as I'm thinking about the control room, and we've talked about distributed energy resources, one area of a lot of research and some new investments right now is in an area called DERMS, which is Distributed Energy Resource Management System. And so this is a kind of a software platform that enables a distribution utility to manage the DER that it has interconnected on its network. It's still very much a centrally controlled paradigm, but it's a software platform that's intended to try to create better management and coordination and visibility when you have more DER.
Gotcha. Before we move on to the other side, let me wrap up two other things. Then we'll move on to the punchline about the demand side stuff. And, first, let's talk a little bit about storage, right? As I was mentioning in our little pregame discussion, I've studied mass electrical storage back in 2004 when it was quite the hot topic. A couple of $1 billion a year were being invested into the area. But my analysis said, not even close to being economical to be able, the case I studied was take overnight nuclear power from northern New England, store it in Brooklyn, and sell it to New York in the middle of the day. You could buy it for half a cent a kilowatt hour. You could sell it for on average about 10 cents a kilowatt hour. So a 20-to-1 markup. In those days, the costs of the batteries were just too high. As you talked about earlier, capital costs. This particular business model was totally dominated by the capital cost per kilowatt hour of storage. And it was off by about a factor of 2. Since then, there have been considerable advancements in battery power, and there's been some development of pump water storage, et cetera. And of course, as you mentioned, this very interesting thing of these electronic vehicles with their big batteries on wheels that have been created for another purpose with a different set of economics, right? They didn't have to make sense for storing mass power, but they might be able to be used for that. What does the storage world look like to you right now, and where do you see it going?
I think you're exactly right that in 2004, the storage technologies didn't have the energy efficiency to be economical. They definitely weren't ready for prime time. And when I teach, energy economics or environmental economics, and we're talking about the cost of storage, and I usually talk with students about different types of storage. So like the battery that you put in your watch or the battery even that's in your phone, what you pay per kilowatt hour for the charge you get to run your device is, probably 1 to 2 orders of magnitude higher than you pay for, that 7 to 10 cents a kilowatt hour that you pay in your house. And so the getting storage to be an economical value proposition has been a real challenge. And I think from a kind of innovation economics perspective, one of the biggest drivers of that has been the development of the lithium ion battery. And so I have to give Tesla a lot of credit for the bringing down the cost of battery production and making the economics of storage much more realistic. And so I think that we're at the point where, because storage is just, it's not a generation technology. It's basically an intertemporal storage technology. You're just shifting, so that you can save some up so that you can use it later. And that in and of itself has a value, and you have to compare it to its opportunity cost, right? The opportunity cost is what's the next best alternative. The next best alternative is I consume from my grid power. And so that's why the comparison is always made to, what do you pay in your house? And so I think the storage is, and it's not just the lithium ion battery. And as you say, the electric vehicle, because the electric vehicle has 2 value propositions. The vehicle can transport me where I want to go. And that's kind of value proposition number 1. But increasingly with a digitized grid, that intertemporal use of your car's battery as a way to store energy for future use in some way other than driving is another value proposition that I think maybe in a few minutes we can dig into in a little more detail. But I think there's all sorts of other storage innovations going on at large scales. And, we can think of hydro, and, hydro is one of the oldest millennia old technology for providing energy that's not human or animal. But hydro generation is itself a form of storage because you can, turn it on and off largely at will as long as you've got enough water. And when you think at that kind of scale, there's other interesting technologies that people are coming up with, like, and I don't remember the name of the company, but there's one that basically has big cement blocks. And
it's called Energy Vault, I believe.
Yes, Energy Vault. Yes, excellent. That you heat up the blocks when electricity is cheap, and then during the day when electricity is expensive, you release the heat. You release the energy from the blocks, and so it's a form of thermal storage. The other one I'm really interested in right now is a company called Form Energy, and they are developing an iron oxide battery, which basically means that the energy storage is by rusting and unrusting a block of iron oxide. So that's pretty cool.
Yeah, I love them. I hope that one works because, as we all know, lithium and some of the other components that are needed in lithium-ion batteries are getting hard to find. I mean, there's enough in the earth, as it turns out, but it's going to be quite a race to get them out fast enough to reach our zero carbon goals.
Yeah, lithium and cobalt. There was a good article in The Economist last week about how the interest in batteries and electric vehicles is driving people to look for sources of lithium and for sources of cobalt that aren't in places like the Congo or China. So, it's a very dynamic space right now.
Yeah, and I expect there will be breakthroughs, whether the iron guys, the Form Energy guys, I think Bill Gates is an investor in them, whether that works or not, somebody's going to come up with some interesting electrochemistries because there's such a gigantic and obvious demand for it, which is very interesting. Now, before we move on to the other side of the question, one other thing I'm going to put forward here is we're talking about a lot of new electronics to make the grid work in this new complex systems environment that it's in, where both production and the consumption is changing radically all the time. It's worth noting and worth thinking about, and hope that people are putting enough attention on this. That makes the grid more subject to both cyber attack and massive failures from exogenous events like massive solar flares.
Yeah, solar flares, terrorist attacks from electromagnetic pulse. There's a substantial attention to cybersecurity in the kind of grid modernization and smart grid focus. And a lot of it, there's some overlap with kind of what I think of as good internet principles. So things like having open standards. I guess I tend to think about these questions from, I guess I would call it a Linux perspective, right? The idea that you have a kind of shared set of code and common interfaces, and then, you design your security around the common interfaces, and that's a better way to achieve security than to have proprietary architectures. Of course, the electricity industry is completely a proprietary architecture industry. Ever since 1895, when Westinghouse and Tesla went up to Niagara Falls and they built the entire Niagara Falls generating station basically as a bespoke artisanal engineering project. And ever since then, it's kind of been this 140 years of one-off type design. And so the idea of standardization, modularity, open interfaces, some of the kind of deep internet principles that we're used to is a cultural shift in this industry. But the cybersecurity is definitely part of the planning and the thinking and the design principles that go into thinking about grid modernization. And some of it I mean, some of it is very deep and very important, having airlocks on certain devices that, just can't be on the internet. And some of it is as simple as, when you buy that digital thermostat, you shouldn't be able to use it, put it up in your home and turn it on. The first thing you should have to do is change the default password. I mean, so some of it's as simple as that, but there is a very wide range of cybersecurity practice. And one challenge, I think utilities are getting comfortable with it, but one big challenge is this is an area that is not very familiar to regulators. And so when the public utility commissioners, when utilities come in and propose, okay, we want this gold-plated consulting company to come in and do our cybersecurity best practices audit. If you're a regulator, how do you have the background to be able to assess whether or not that's a prudent investment? And so getting the kind of cybersecurity utility regulator, public interest, public service constellation all lined up, I think that's going to be a big challenge, is just getting the information and awareness promulgated.
Yeah, and those culture change things are harder than they sound, right? These people
Yes.
they've been doing a good job. I mean, our electrical grid in the United States and Canada is remarkable on a worldwide basis. And so they can rightly pat themselves on the back, saying we've kept the grid up for 100 years with a few intermittent failures, but overall pretty damn good. And you're asking us to change. That could take a while.
Yeah. Cultural change is definitely challenging, and especially when it's in an area where you don't have subject matter expertise. And a lot of these digital technology and, especially the cybersecurity issues, it's like, we know that we don't know that, but that means that we don't necessarily know how best to find a path forward. So that is a challenge. Yeah.
All right, well, let's now move on to where the story gets even more interesting. You and some of your collaborators have worked on an idea called TESS, the Transactive Energy Service System platform. And as I understand it from your presentation at SFI and some reading I did yesterday and today, one of the key ideas here is that the demand side also becomes automated and can communicate over the network and do stuff. Is that one of the core interesting ideas that's added now to the mix?
Yes, and that exactly. And I mean, for just speaking as a researcher, my interest in this topic came out of a topic, and this goes back to the 1960s, well before my time, but certainly by the time I was working on this in the early 2000s, there was a very rich economics literature and very rich policy conversation around dynamic pricing, and the idea that it would be economically beneficial to have pricing to retail customers that more closely matches the way costs vary over time. The way we discussed that, at 3 a.m, generating electricity is cheap, and at 5 p.m, it's expensive. And there's, with the old style peakers, there was more emissions, and so it was also more environmentally costly. So what if we had dynamic pricing that allowed prices to vary in ways that more accurately reflected actual costs? And so that dynamic pricing conversation had been going on since the time of Marcel Boiteux in the early 1960s. But by the 1990s, and certainly around the period of regulatory restructuring in the mid 90s, there's a lot of conversation about fixed prices are one of the vectors of inefficiency in the regulated system, and we need more dynamic pricing to give better information and better signals to consumers so that we have better demand side incentives. And at the time, we didn't yet really have digital technology on the radar. But then by about 2004, 2005, and we all are starting to have these cell phones not smartphones yet, but cell phones. And so you have digital technology in your pocket. And so, if you're on the train on the way to work, you can receive a text message that tells you, hey, it's 8 a.m. tomorrow at 8 a.m. Here's what the price of electricity is going to be. And so you could program your thermostat, go home that night and program your thermostat to, take advantage of some of the cost saving opportunity that you have. And so that's, I think, kind of one of the origin stories. The other origin story is at about that same time period, I was working with Vernon Smith, who is an experimental economist who in the 1960s founded the field of experimental economics. And in 2002, won the Nobel Prize in economics for his work. And shortly after that, he and I were working together and trying to work with regulators to have them use experimental economics as a way to test bed some of their regulatory design proposals or market design proposals before you actually release them in the wild. And this is when we were all still very much having the hangover from the California electricity crisis, when too many market designs were released in the wild without proper testing, and a lot of people suffered the consequences of that. And so experimental economics is a paradigm. It's a methodology in economics where you create a laboratory setting to test a specific hypothesis. And so in this case, it might be a market hypothesis. And so, you divide half the room into buyers, half the room into sellers, and you tell the buyers what their values are. You tell the sellers what their costs are. Most importantly, you tell them what the rules are in the market, and then you let them trade and see what happens. And then you might run another treatment where you use a different set of rules and you see how that set of rules performs versus the first set of rules. And so I think if you put these together with digital technology, that's where you get this idea of TESS or transactive energy, that you can automate your energy related devices in the home to respond to price signals. And, the kind of received wisdom in electricity is, people don't want dynamic prices. They don't want to have to sit there and twiddle the thermostat to try to save money. And the beautiful thing about digital technologies is that it reduces those transaction costs because you can automate your preferences into your thermostat. Basically, have some algorithm that you just plug it right in and say, okay, here's how I want you to behave. And then it can turn that into bids. And, in this particular time period, my thermostat is willing to pay 8 cents a kilowatt hour for that electricity. And so you submit that as a bid. And so your thermostat, your EV, your water heater can participate in a local market on your behalf without your having to stand there and do the work manually.
Yeah, and in fact, you don't probably even have to worry about the price too much. You might set some parameters, like you'd say, make it so it 99.99% of the time doesn't get any colder than 65 in my house. And you figure out how to do it, right? As an example of the kind of interface that a human could understand, which could then be converted into bids behind the scenes by the right software.
Yeah, and I think my collaborators and I haven't done this, but I think it's one of the next types of things that we will do is, rather than putting, because I think of it, very Boolean, here's the temperature set point I want. And if the price goes above, say, 9 cents, then change my temperature set point by 2 degrees. Right. So I think of it in that very Boolean way, but it may well be that more the way you just described is very amenable to a machine learning approach. And so I suspect we will see more of that kind of machine learning, just, gathering data about what's going on in the market and then taking your parameters and basically fitting your parameters to get the kind of best joint outcome of whatever you want in terms of savings on your bill, or how much of what you're consuming is a low carbon, whatever your preferences are. I think machine learning will be an approach that does what you just described.
Yeah, I think that makes a lot of sense. Now, you mentioned the need to test, right? Because one of the things that we know about complex systems is you can't really get there by static mathematical analysis, particularly where the players are, in general, but even more so where the players are agentic. People who they have personal goals. I want to save money on my electric bill, but I don't want my toes to get cold in my living room, right? Or the person on the other side who's trying to maximize their profit. And so when you have, network competition between agentic enterprises and many of them coming and going through a intermediation platform like a grid and a market attached to a grid, you can't really know what's going to happen, right? How do you test for something like that?
I think you're exactly right. And you said it really well, because usually the way I say it is much more jargony. It's because once you have all of these, agentic, these agents with their own individual preferences, and their preferences are subjective and they're private, they're personal to them. I don't know what the trade-off is for you between, warm beer and cold showers and saving money on your bill. I don't know that, know that. And that's true for every single one of us. And so when you take all of these many, many, many people with their private subjective preferences and their own projects, and you put them all together and they're all using this electric system as an input into the variety of things that they want to do, it's a very complex system. I mean, and technically speaking, complex meaning not deterministic. You can't necessarily begin at point A and deduce your way to a known specific certain outcome, right? And so how do you test in that kind of environment? What my collaborator, David Chasson, who's at SLAC National Laboratory at Stanford, he, several years ago, when he was at Pacific Northwest National Laboratory, he wrote an agent-based modeling platform called GridLab-D. And so that's what he and his engineers use, is they use GridLab-D as an agent-based modeling platform. And so in agent-based modeling, what you do is you're defining who all the agents are. And so in this case, it would be like, okay, suppose we have 100 houses, and we can say how big the houses are, how many kilowatts of electricity capacity they usually consume, and suppose we have a couple office buildings and some other stuff. So we have this system with these agents in it, and then we put solar panels on top of half of the houses. And so they now have a production capability, and you basically then set some parameters and run the model. And so it's not a closed form. And I come from economics. So for an economist, in theory, mathematically, we're always looking for the closed form solution, right? So here's my mathematical model. I'm going to solve for P star and Q star for, equilibrium, price, and quantity. And I'm going to get this nice closed form solution. Whereas complex systems are very open form. And because they're not deterministic and nonlinear, you can't do that closed form kind of calculation of equilibrium. So agent-based simulation and just running thousands and thousands and thousands of iterations, and then you change the parameters and run thousands and thousands and thousands of iterations. So it's a more inductive, or I guess if I'm channeling my Charles Peirce, late 19th century philosophy, I would call it abductive way. It's not deductive, because you can't necessarily get to that single deterministic, here's the solution we're going to get. But you can basically get an inductive/abductive idea that, 95% of the time, the solutions we're going to get are going to be in this range from A1 to A2.
Gotcha. Yeah, for people who want to learn more about agent-based modeling, we had a really good episode back on EP90 with Josh Epstein, where he went really deep in agent-based modeling as applied to the social sciences. So there's another resource for our listeners out there, because this is a fascinating field, one that we use a lot at the Santa Fe Institute. Okay, now the other thing, of course, you can do is smaller scale experiments. You were involved, I believe, with the Olympic Peninsula Testbed Project?
Yes.
Why don't you tell the audience about that?
Sure. And this was, again, back in the mid-2000s. And at the time, I was working with Bernard Smith. We were doing experimental economics, very much focused on test bedding, market designs, and policy designs before they go out in the wild. We went and did a study session at Pacific Northwest National Lab right at the time when they were starting to develop this idea of transactive energy. And they were working with Bonneville Power Administration. Bonneville's a big federal hydroelectric facility in the Northwest, and they operate a big transmission network and then connect up to a distribution network to go out to the local public utility districts out on the Olympic Peninsula, way up in the northwest corner of Washington State. And the public utility district up there, the PUD, was doing their demand forecasting and finding that they were expecting their demand to increase over time because it's a very beautiful place. It's lovely, pristine. People wanted to move there. But they were concerned that they would soon exceed their distribution feeder wires capacity. And, it's beautiful and pristine. And most of the surface area of the Olympic Peninsula is also a national park. So the last thing you want to do is do the traditional utility thing, which would have been to, quote unquote, put iron in the ground and build a power plant. And so they were working with P&L and Bonneville to think about other approaches to better match supply and demand. And so they were starting to think in what we today would think of in terms of demand flexibility. How can we harness demand flexibility to be a better match with, given our supply constraints? And so we were out doing an experimental economics session and did this double auction market experiment. And the P&L engineers were like, oh, hey, that looks like it would fit really well with what we're trying to do in this project with Bonneville and the local PUD. So I started working with them on this Olympic Peninsula Testbed Demonstration Project. And it was a field experiment. And the field experiment had two components, at least the portion of it that I'm going to describe here had two components. One was, so we had 130 households participate, and every household received a digital two-way programmable communicating thermostat. And this is in kind of 2005. So your kind of most common digital thermostat at the time, if you went to Home Depot and bought one, you'd be able to program in particular time slots. So I want to go to work at 8, so turn the heat temperature down. I come back at 5, so turn the heat temperature up, and that kind of thing. This programmable thermostat had much more digital intelligence embedded in it, and so we could program in their contract choices. And that was the second component of the experiment, was that they could choose, they got to select from sort of most favorite to least favorite which contract type they wanted, whether they wanted to have a fixed price contract, a time of use, peak off peak contract, or a real-time price contract. And then we had a control group that only had the thermostat, and they just, the kind of contract experiment was a layer on top of their existing bill. And we allocated each of them to one of the treatment groups in the contract, and then we had this control group that didn't have any particular contract layer on top of their existing bill. So I mention all of that just to say, this is a pretty standard laboratory experimental design. But what was interesting was, we wanted to randomize take the 110 households that weren't going to be in the control group and randomize them across the 3 different contract types, but the utility wasn't so keen on that idea. So we asked them to pick which one do you want to be in. And interestingly, after learning about, we prepared educational materials, about 2/3 of them wanted to be in the real-time price group. And this just completely runs counter to the received wisdom in the industry, right? Because the received wisdom in the industry is that, people don't want price variability. They want their bills to be low and stable, and they don't want price variability. But of course, what's true now, if you have a digital technology that you can use to control and manage your bill by responding to prices without you're having to be there, twiddling the thermostat yourself, you're like, hey, the thermostat can do this for me. So sure, I'll take the real-time price. So anyway, we divvied them up into the three groups and ran them for a year. I was in charge of designing the real-time market, and we did it as a double auction. So each of the thermostats of the participating households, they could each submit a bid and it was every 5 minutes. So the bid is essentially the thermostat communicating into the market, here's what I'm willing to pay, here's what I'm willing to pay, here's what I'm willing to pay. And different people would set different thresholds, right? So different trigger prices. And so you would get responsiveness, demand flexibility out of having those thermostats participating on behalf of their owners in this local energy market. And it worked really well. They saved the real-time market, they saved about 20% on their bill. They had a slight overall increase in their energy consumption, but the system also did a really good job of managing the wire's capacity constraint. And so that was the origins of Transactive Energy. And ever since then, my collaborator Dave and I have been working to keep moving along with this, because it is a very original approach to demand flexibility. And now with these distributed energy resources, there's a lot more going on than just thermostats and water heaters.
Indeed. Now, on the flip side of it, you hear horror stories like the big freeze down in Texas where people got $30,000 electrical bills, et cetera. Now, could it be that there's a power law distributed or fat tail distribution of the effects of these market-based systems, and that if you took a long enough time frame, maybe people wouldn't be better off, and particularly those people who are averse to a big financial shock?
Yeah, I do think that was the Winter Storm Uri in 2021 was a big learning event for everyone. And the Texas legislature has essentially taken the type of market that I just described that we did in the Olympic Peninsula, and they have made that illegal, which I in my opinion is throwing the baby out with the bathwater. And I think actually I have so many thoughts about this, I'm not quite sure where to start. There were really two retail companies in Texas that were offering residential customers a real-time price wholesale pass-through type contract. One was called Griddy and one was called Octopus Energy. And Octopus Energy did, I think they kind of had a little bit of a better financial hedge situation. And so they were able to say to their customers, all right, we're going to cap your bills. You're only going to be responsible for a certain portion of this high run up in the bills during the winter storm. Whereas I don't think Griddy was in that kind of financial position. The thing that really breaks my heart is that Griddy had already announced to their customers that they were going to be introducing an insurance product. Right. And I think, right, if you take the analogy between buying electricity and having that price variability and buying a plane ticket, right, where you have some probability that your trip might get canceled and you don't want to get stuck holding the bill for that plane fare. And so what do? You buy your plane ticket and you buy, non-refundable because it's cheapest. And we've all learned since 1978 that that's how airplane customers behave, is they buy the cheapest ticket. But then you buy a travel insurance contract on top of that. And so I think that's one approach that you can take. And it's kind of like you were saying earlier about sort of guardrails or setting your parameters so that, your comfort level never, temperature never goes above this or below this. You can also do it so that your spending never goes above this or below this. And one way you can do that is by having this price insurance that you layer on top of the real-time market. And The problem with Griddy was that they were going to start selling that insurance contract to their customers on March 1st, and the storm was February 14th, and then they went bankrupt. So I think the challenge for places like, or situations like that Winter Storm Uri, is twofold. Number one, getting the financial instruments and financial markets right so that you have enough opportunities for parties to hedge and to basically lay off risk on people who are willing to bear the risk. And residential customers, for the most part, are not willing to bear a whole lot of risk. But at the same time, create an opportunity for them to choose to accept price signals, because we know that those price signals enable them to save money, for which they have to take some risk. But that also better aligns their behavior and their incentives with the underlying true actual costs in the system. So I think it's a tricky situation, but just outlawing a wholesale pass-through real-time market is not the right approach.
Yeah, this is what economists would call institutional design question, right?
Precisely.
So you talked about that a little bit. What you, as a economist who has spent at least a fair part of your last many years working in this space, what are some of the things that regulators, practitioners, the public should keep in mind when thinking about institutional design to be able to take advantage of this new opportunity?
Yeah, it's a good question. It's a multifaceted question. And part of the challenge is, I think, because we are coming out of our 20th century experience, right? So I think our reaction to technological change is very historically contingent, right? So we're used to this 20th century, large scale central generation, centralized control of what goes on in the grid. The users around the edge, around the distribution edge, are just passive consumers, and they flip the switch and the light goes on and pay a fixed price and don't think about it. Whereas now, the technology landscape is so different, with so much more diverse generation technologies, the increasingly economical storage technologies, all the digital devices that we have to control and automate our response to all sorts of things, including price signals. So it's a very different landscape, but yet our preconceptions about regulation and regulation's role as consumer protection and the utility as vertically integrated monopoly, our preconceptions around all of that are slower to change than the technology is. So technology is way out ahead of us. And I think the institutions evolve more slowly. And part of that is just, humans' discomfort with risk and, kind of defaulting to the status quo. And the thing that is, I think, going to be important and challenging is a kind of willingness to reevaluate those hard questions. Like, with these new technologies and the way they change the economies of scale and generation and economies of scope, and the way they change what consumers can do and how consumers can use digital technologies to compare prices and protect themselves in the sense of consumer protection, how should the regulatory footprint change? Right? Should the regulator, what should regulation be doing differently, and how should it be doing it differently? That's, I think, one of the fundamental regulatory institutional design questions. And then on the flip side of that, the utility business model is, the vertically integrated firm where the generation, the wires, and the retail are all in one firm. That's an artifact of the early 20th century. And in some states, it's been kind of chipped away on the generation side, because in some states, we have wholesale power markets because of the technological changes of things like the controlled cycle gas turbine, making, generation markets more competitive. But in many states, they still have that vertically integrated footprint. And whereas the underlying economics would suggest that the utility business model should really match what we call the natural monopoly footprint, right? The places where regulation is still deemed to be an important protection against monopoly behavior. And so, the implication of this is that the utility footprint should shrink utilities should shrink to become the best possible wires company that they can. And the rest can all be done through competitive markets. And those markets still have to have some design. Markets require rules, and rules emerge organically, but they also are designed and they change over time as conditions change. So it's a very dynamic, the institutional design is a very dynamic and fluid thing in this industry because you're coming from this preconception that's so heavily administered and regulated.
Yep. And yet we do know it's possible because, as you point out, several states have gone to wholesale power generation, and I think generally it's worked, hasn't it?
It has generally, and nothing is ever perfect. And I think this was one of the failings of the California restructuring leading into the California electricity crisis in 2000, 2001 was this kind of benchmarking of the notion of quote unquote perfect competition. And I think we've learned a lot in the 23 years since then. And that, having a little more epistemic humility, realizing that we can't know it all and we can't achieve perfection, but that we can do something. And my favorite thing to do here is to quote former Texas PUC chair and FERC chairman Pat Wood, who is very fond of saying that competition on its worst day will do a better job of protecting consumers than I did as a regulator on my best day. So, I think that's for me, that's the right benchmark, right? It's not the perfection, but it's the compared to what, right? So compared to regulation, how well do these markets do? And, I have a litany of institutional design critiques I could make of wholesale power markets, but in general, they have performed better than the counterfactual of had they stayed in a vertically integrated structure.
It seems to me, just sort of think about this a little bit. One potential role for the regulators is to, require that the institutional designs trim off the tail risk for people who aren't capable of bearing tail risk. The big fluctuations on the rare event. Your grandmother gets a bill for $30,000. The regulator should make sure that the system has things like you described, which is an insurance policy that in the aggregate works fine for big insurance companies and Wall Street firms that want to back that pool, and they can afford month to month or year to year fluctuations, so long as the nickels and dimes add up to more than the hits over time, while grandma doesn't get exposed to the once every 100-year chance of a $30,000 electric bill. That doesn't seem too hard to envision.
Yeah, I think that's exactly right. And it's a lesson that we learn by looking across different industries. And so, if you look at financial markets or some other industries, you can think in terms of this tail risk framing that you just articulated. But that's a new framing and a new mindset in an electricity regulation context. So I think that's exactly the right way to go. And I think it's up to those of us who work in this space to help move us there.
Yeah, and I will pound the table on one of my pet peeves. One of the reasons people in traditional analytical frames don't get it is they tend to think in terms of Bayesian statistical distributions, bell curves, right? And you can say, oh, this is a 7 sigma event. It'll happen once every 10,000 years. Well, wrong, people. A tremendous number of emergent complex systems fluctuations have turned out to be power law distributions, much fatter tails. Right? This was, I still recall being almost wanting to throw a knife at the TV back in 2008, where some CEO of a big financial services company says, how could we be held responsible? This was a 16 sigma event, i.e. once in the history of the universe, right? When if you looked at it from a fat-tailed, a reasonable fat-tailed distribution, distribution analysis, it came out to about once in 100 years, which is almost exactly what it was, right? Since the next biggest one since the Great Depression. So, people locked into the statistics 101 Bayesian analysis tend to not have a good intuitive feel for tail risk.
I will join you in pounding the table on tail risk.
Indeed. Well, there's lots of other interesting things in your work, but I think we're just about up to our time. I really want to thank you for an extraordinarily interesting session about the grid and where it may be going.
Thanks, Jim. I really enjoyed the conversation.
Audio production and editing by Andrew Blevins Productions. Music by Tom Muller at modernspacemusic.com.